So today we're going to be talking what's called a series. So a series is just the sum of a specific number of terms in a sequence. It's comparable to sigma notation, which we have done in the previous class. Let's take a look at the series we have here, or the sequence. We have the sequence 5, 8, 11, 14. If you look closely, you'll see that the pattern from term to term appears to be that you add 3, making this an arithmetic sequence. Meaning if we wanted to find any term in the sequence, it is the first term plus the common difference times n minus 1. In this case, the first term is equal to 5, and the common difference was equal to 3. If I were asked to find the sum of the first 1,000 terms of a sequence, I would have to use sigma notation, write n equals 1 up to 1,000, meaning from the first term to the 1,000th term. And I would just write the formula for the sequence into the sigma notation, and I could use a calculator to determine the sum of those terms. So we're going to do that now using the calculator I have on this iPad here. We're going to do math sigma notation. I'm going to say x is equal to 1 up to 1,000 for 5 plus 3 times n minus 1, or x minus 1 in this case, and we'll get 1,503,500. So that is the sum of the 1,000 terms of the sequence. Now this can also be accomplished using another method, which might be more helpful if your calculator that you have access to at the time does not have summation notation. It's a different formula. I'll show you it in just a moment. So the way this is going to work is that if I have a list of numbers, let's say we'll use the sequence that we were given, 5, 8, 11, etc., all the way down to the last number, the 1,000th number. So this is term 1, term 2, term 3, and so on. At some point I will eventually reach the 1,000th term. So the 1,000th term will be 5 plus 3, 999 times. So let's see what that is equal to. So we start at 5, and we're going to add 3, 999 times to find the 1,000th term. That is 3,002. So another method for finding the sum of these terms is something that was discovered by a mathematician named Charles Gauss. And the method that he used, which is pretty interesting, is to write the sequence backwards. So I'm going to write 3,002 here. That means this should be a 5 here. The second to last term in the sequence would have been 2,999. The term before that would have been 2,996. And so on for every term in the sequence. And that means this is the 1,000th term, this is the 999th term, this is the 998th term, until we eventually get back to the first term. So what he noticed is that if you were to add these in pairs, they all give you the same outcome. They all add up to 3,007, the first term plus the last term. And that's going to happen for all 1,000 pairs of the sequence. And if you were to count how many of these sums there were 1,000 of them. So this could be rewritten as 1,000 copies of 3,007, which would be equal to 3 million and 3,007,000. And that's not the same sum we got a minute ago, and the reason for that is we added the sequence to itself twice. So this is actually double the value of our sequence. So if we just take that number and divide it by 2, we will get 1,500,000, 3,500. So we get the same sequence using this method. So the specifics of this method, like ignoring the numbers in the problem, is basically you take your first term, so we call this Sn, meaning the sum of the sequence, So Sn is equal to the first term plus the last term, or an, which you do need to calculate. So an needs to be calculated using the formula to find whatever the term is. So if we were looking for the 1,000th term, we'd be looking for A1000. So we'd add those up, multiply them by whatever number of terms you have. So if it was 1,000, we'd multiply by 1,000, and then divide it by 2. So this is the formula for the sum of an arithmetic series of n terms. There is a second formula that doesn't require you to calculate the last term in it. I wouldn't recommend it, but you can do it. It is Sn is equal to n times a1 plus a1 plus d to the n minus 1. In other words, this is just, you replace an with the last term, which is a1 plus the common difference times n minus 1. All of this is then divided by 2. So essentially it's the same formula, just that you put the formula for calculating an into the formula itself, and this simplifies to be Sn is equal to n over 2 times a1 plus a1 is going to be 2a1 plus d times n minus 1. So there are two formulas to use. It doesn't really matter which one you use. You can use this one if you're willing to calculate the last term yourself, and you can use this one if you're not willing to calculate the last term yourself. So that is to find the sum of any number of terms in a sequence. You can also use this to find the sum of a portion of terms in a sequence. So if I asked you to find let's say I give you this sequence, 1, 2, 3, very obvious, easy one, and I told you to add the 5th through 9th terms, we can do that as well. It would be our first term, which is 5, plus our last term, which is going to be 9, divided by, multiplied by the number of terms we added, which is 4, all divided by 2. So the sum of 5 through 9 would be, 14 times 2, which would be 28. So this would add specifically the 5th term to the 9th term. Oh, the number of terms was 5. Oh, okay, whoops. 5 over 2. So it'd be 5, 6, 7, 8, 9. So 5 plus 9 is 14. 14 times 5 would be 50, plus 20 is 70, divided by 2 would be equal to 35. So that was the first term of the sequence I was being asked to add, plus the last term of the sequence I was being asked to add, times the number of terms in the sequence divided by 2, which is just the rule for adding a finite or non-infinite number of terms in an arithmetic sequence. So this worked because this is part of an arithmetic sequence. All right, let's move on to geometric sequence. So here's a geometric sequence. It is 3, 1.5, 0.75. So you can see that it multiplies by a half. So the sequence would be written as an is equal to 3 times 0.5 to the n minus 1. And if we wanted to find the sum of the first 25 terms, we would have to write n equals 1 to 25. And we would just put in the sequence formula. And we can calculate the sum of the first 25 terms of this series. So it would be called a geometric series. And there's also a rule for adding an infinite geometric series, specifically when the common ratio is less than 1, but bigger than 0. So we'll cover that in a moment as well. So we're going to use our calculator and see what the sum of those numbers are. So I'm going to type in summation of x is equal to 1 up to 25 for 3 times 0.5 to the n minus 1 power. And we get 5.99999. All right, so 5.99 is approximately 6. So this was approximately equal to 6. Now, if we were asked to add maybe the 10th to the 15th term, you would just rewrite the formula to start at whatever the 10th term was, times the common ratio to the n minus 1 for the remaining number of terms. So we can kind of do what we did before. Now, there is a secondary rule you can write, so you don't have to use summation on a calculator to do this. You can write A1, which is your first term. This is all equal to Sn, so the sum is going to be equal to A1 times 1 minus r to the nth power. All of this is over 1 minus r. So if I were to use this sequence for an example, Sn would be equal to 3, because that's our first term, times 1 minus 0.5, because that's our common ratio, to the 25th power. All of this would be over 1 minus 0.5. So we'll just use a calculator and see if we get the exact same answer. We should get 5.999999 and so on. So we'll type in fraction mode, so alpha y equals to get access to the fractions. I'll type 3 parentheses 1 minus 0.5 to the power of 25. All of this is going to be divided by 1 minus 0.5. I think I left out the decimal by accident, excuse me. So 0.5. Let me put that decimal in here as well. And if we press enter, we get the exact same answer. So this formula works as well and is useful if your calculator doesn't have access to the summation feature. So that was also equal to about 5.99, which is equal to 6. And in the event that we're adding a geometric sequence, again, this is called a geometric series, we can actually add every term of the sequence, all infinite terms, if the ratio is decreasing, meaning less than 1. So let's say I wanted to use this same sequence, so 3 times 1/2, and I'm just going to add all infinity terms. The rule for adding infinite terms is Sn is equal to whatever our first term is, times 1 over 1 minus r. So it's almost the same formula, the only difference is that the numerator is just 1 inside of the fraction here. So we're just going to calculate this for our example. We'll get Sn is equal to 3 times 1 over 1 minus 0.5. Now, I'm under the impression we're going to get 6 because it seemed like the example was getting closer and closer to 6. But let's calculate it ourselves. Alpha y equals, to gain access to fractions, I'll type in 3 parentheses 1 over 1 minus 0.5, and don't want to miss the decimal, and we get 6. So while the first 25 terms added up to 5.99, which was approaching 6, if you were to keep adding these smaller and smaller decimals, they will eventually add up to exactly 6. So that's going to wrap up this video. If you have any questions, I will see you in class.